Mr. President and members of the jury for accepting to review my thesis defense today. And good morning, everyone. My name is Carla Barcelo Chong, and today I will be presenting my thesis defense on the subject of the spray drying of biopharmaceutical drug products. This thesis was performed under the supervision of Mrs. Ray, Mr. Nakash, and Mr. Philip from the Ramsey Center of the Codeminali and the company Soutenance. To guide you through this presentation, we have the following outline. I will start presenting the context and objectives of this work, followed by the main parts that were done to achieve these objectives. The first one will be focusing on a model protein. The second one and third one will be for the protein of interest, which is a monoclonal antibody, before concluding this work. First, I would like to set up the context for the realization of this thesis. With the recent technological advancements in the pharmaceutical industries, there's an increasing interest in the production of biopharmaceuticals, given their targeted activity and the reduced side effects. To obtain these pharmaceuticals, we use organisms or functional parts of organisms, and we retrieve them by using biotechnological techniques. Some of these products can be DNA, cell culture, blood plasma, and most interesting proteins in this case. The proteins have gained recent interest. For example, in the USA, in the year of 2015, were already around of 30% of the registered drugs from the FDA, the protein-based biopharmaceuticals. Within this category, we also have what we call monoclonal antibodies, which in the year 2021, they had a worldwide increase of 30% in the late-stage commercial clinical pipeline. The monoclonal antibodies are large heterodimeric molecules, and the interest in this type of molecules is their very high targeted activity, as well as their wide therapeutic range for chronic diseases, for example, cancer and immunogenic and inflammatory diseases. And the importance for the therapeutic effect of this protein is that they keep their stability. And this stability will depend in many factors, such as the pH, temperature, molecule composition, the isoelectric point, and the formulation in which it is contained. For this thesis, the monoclonal antibody will be named monoclonal antibody A. And one of the challenges when producing monoclonal antibody formulations is that they are mainly in the liquid state. Therefore, they are in a very mobile environment, which generates protein-protein interaction, which leads to aggregation phenomena. And this can lead to a lower shelf life and to the application of a cold chain during the production, which uses very low temperatures. To tackle this problematic, we can perform a change in the formulation physical state to pass from a liquid to a powder formulation by using drying techniques. With this, we can expect to extend the shelf life and as well to reduce the cold chain and the temperatures used during this one. And to achieve this, we reduce the water content in the formulation, which will lead to a reduction in the mobility of the protein and therefore reducing the phenomena of aggregation. Some of the drying technologies that we can have are drum drying, electrospray drying, freeze drying, spray drying, and spray-free drying. In the pharmaceutical companies, we will focus mainly in these three ones: freeze drying, spray drying, and spray-free drying. One of the motivations for this thesis is that one monoclonal antibody formulation was dried using these three different techniques, yielding different results. For example, for freeze drying and spray-free drying, the formulation we obtained produced a very high quality formulation that after reconstitution had low aggregation and turbidity. On the other hand, for the spray drying process, the formulation that we obtained showed to have high turbidity after reconstitution from the spray dried powder and as well aggregation. Therefore, for this thesis, we will focus on the process of spray drying to understand the effect of the different stresses on the protein stability. Firstly, I would like to introduce the process of spray drying. During the spray drying, we will have the spraying of a liquid formulation through a nozzle into a drying chamber by using a spraying gas, in this case, air, and as well using a drying gas that will get in contact with the spray, and it will dry it to form a final dried particle that we will recover with a cyclone for further analysis. In this type of drying techniques, previously I mentioned different drying techniques that present different combination of stresses. In the drying technique, the stresses that we have present in the different steps can affect the protein stability. The stresses that we have in this process in specific are the shear forces, the interfacial stresses, and as well the thermal and the hydration stresses. One way to tackle the effect of these stresses are by manipulating two parameters, such as the process parameters like drying temperature, liquid feed flow rate, nozzle diameter, or as well the formulation composition to give protection to the protein during these steps. Firstly, we can have, for example, for two stresses like shear forces and interfacial stresses, what we call the competitive absorption theory. This is given by excipients such as surfactants and amino acids. In this case, what this theory tells is that the excipients will come to the surface of the droplet and will replace the protein molecules that are present in this part, therefore making them to go into the center and core of the particle, avoiding the contact with the stresses generated during the shearing in the nozzle and interfacial drying air. Then, for the thermal stresses, we have the vitrification theory, in which we'll form a glassy matrix around the protein to protect them from the temperature generating during the spray drying process. This one is given mainly by sugars. And finally, for the dehydration stress, we will have the water replacement theory. This theory explains that the excipients such as sugars and amino acids will come replace the hydrogen bond between the protein and the water molecules to preserve the protein integrity and structure to avoid denaturation. Besides the stresses generating during spray drying, when we are in the liquid state of the formulation, we can have the interactions between the proteins. Therefore, to avoid this, we have what we call the preferential exclusion theory. And this one is given by sugars, which will recreate repulsion between the molecules, the protein molecules, and avoiding the aggregation phenomenon. Now that we set the context, now we will go to the objectives to tackle this problematic. What we want to do is to pass from a liquid formulation by using a spray drying process in a lab scale, measuring the different stresses that are present on the protein aggregation, to finally produce a spray dried powder that, when reconstituted, is in a stable form. The thesis approach for this is divided in three main parts. The first one corresponds to the study of the model protein in a formulation without excipients, and doing the decoupling of stresses during spray drying process, as well as the study of the spray drying per se. The second part, what we will do will be the analysis of the molecule of interest, which is the monoclonal antibody, by doing the study, again, of the decoupling of the stresses, and doing also a study of the different parameters of the spray drying process and the formulation composition. After this second approach, what we will do is a formulation optimization from the information already gathered. Now we will pass to the study of the model protein. What we chose as model protein is BSA, or bovine serum albumin. The criteria for the choice of this protein is that it's very reported in literature for spray drying processes. And as well, the interest to use a model protein was to study the impact of the stresses in a formulation without excipients, and that there is no current information in the decoupling of stresses study in the setup that we choose. The formulations that we are using for this part are at two different concentrations, 100 and 200 milligrams per ml, reconstituted in milky water without excipients. Then the setup and methodology for the decoupling of stresses will be containing three parts, three sections. The first one will be the performing of the spray drying process, and then the decoupling of two stresses. First, the shear stress in the decoupled shear stress test, and secondly, the thermal and the hydration stresses. The different products obtained from these different tests will be characterized for the powder, for example, the particle size distribution, imaging, and moisture content. This powder will be reconstituted using milky water to achieve the first initial protein concentration and to obtain what we will be calling the reconstituted solution. This reconstituted solution will be characterized in terms of aggregation and physicochemical characteristics. The aggregation in this case will be followed by dynamic light scattering, which measure the hydrodynamic diameter of the molecule suspended in the reconstituted formulation by measuring the zeta average value. And the second one will be the turbidity using the nephelometric turbidity units, given that the presence of the opalescence that can be measured by turbidity is mostly related to the presence of aggregates in the formulation. Now, I will present firstly the shear stress test. For this test, what we did is using the setup of the classical spray dryer, and what we performed was the spraying of the liquid formulation without any drying gas coming into the drying chamber of the spray dryer. And finally, what we obtained here is a sprayed formulation in liquid state, ready to be characterized. And in order to measure the impact that this process has on the protein in a numerical way, we have two different parameters. The first one is the shear stress, which is related to the viscosity of the formulation. And the second one is the strain history, which is related to the time of exposure that the formulation has when passing through the nozzle. Both parameters are related to the shear rate values that are taking into account the velocity of the gas and liquid feed flow rates and the nozzle diameter, for which we are using the geometry of the bifluid nozzle of our spray dryer. This is the setup used. It's a Buscemini spray dryer, B290, in the conditions mentioned here, remembering there is no drying air, therefore we're using the room temperature. And the shear rates generated for this test were around 10 to the 5, which are usually found in lab-scale spray dryers. From the results obtained in this test, in terms of aggregation measured by dynamic light scattering, showed that the impact of the shear stress for a protein concentration that is lower, in this case 100 milligrams per ml, it's very, very slight, while for a higher concentration we can observe a slightly higher impact of the shear stress on the protein aggregation. And now we will pass to the thermal and the hydration stresses test. This test was performed using the setup of a single droplet drying generated for the thesis of Sousa Lima. In this case, this setup consists of a chamber where we have a filament where we can suspend a droplet that will get in contact with a drying air. The filament is attached to a scale and it's observed by a camera, which allows us to follow the drying kinetics of the droplet from the initial droplet to the final dried particle that will be analyzed. The conditions for this test: the temperature was set up to 72 degrees Celsius and the time of exposure was around 1 hour to allow the final dried particle to arrive to very low moisture contents. The results from this test showed that the thermal stress had a higher impact on protein aggregation compared to the shear stress results on aggregation. This is the final particle that we recover after the test to be characterized. Now that we studied the decoupled stresses impact on the protein aggregation, we will study the spray drying process, which coupled these both stresses. The drying condition temperature was set up at 105 degrees Celsius, and the results obtained for the powder characterization of the BSA, we have that for both concentrations, we obtain very close values for moisture content and as well for the particle size distribution. As we can observe in the same images, for both different concentrations, we obtain very similar morphologies for the particles. In terms of aggregation, we can observe as well that we have similar results to the ones obtained for the shear stress test. Again, the concentration that is higher, therefore 200 milligrams per ml, shows to have a higher impact on the presence of the aggregation during this process. I want to also notice that the aggregation obtained for the spray drying is slightly higher than the one obtained for just the decoupled shear stress. And for conclusion of the part of the model protein, what we have is that for a high concentration protein formulation without any excipients, the shear stress test has no so significant effect on the protein aggregation. Meanwhile, the decoupled thermal stress showed to have a very significant effect on the protein aggregation. And in this part, I want to tell that the exposure times used in the thermal dehydration stress are higher than the ones we encounter in the spray drying process, which show to have a slightly lower aggregation than the thermal stress, well, a high lower aggregation than the thermal stress. But the exposure times in spray drying are lower than a residence time of around 2 seconds in the drying chamber. And now that we studied the model protein in the decoupling of stresses without any excipients, we will pass to the study of our interest molecule in a formulated solution. We will divide this experimental part in 3 different sections. The first one will be the decoupling of spray drying stresses, as well as we did for the model protein, followed by the study of the impact of the spray drying process parameters. And finally, we will measure the formulation impact on the map stability. The characterizations performed in these 3 different sections are the same ones that we performed already for the model protein in terms of powder characterization and reconstituted solution. From the decoupling of stresses performed for the monoclonal antibody, we will use the same setups used for the model protein and the same conditions for each one, for spray drying, for the decoupled shear stress, and decoupled thermal dehydration stress test. But in this case, the formulation we are using, it's containing our monoclonal antibody at a concentration of 100 milligrams per ml using 4 different excipients, histidine, arginine, triallose, and polysorbate 80. And the global results obtained for this decoupling of stresses for the monoclonal antibody show different results than the one we observed for the model protein. In this case, in this formulated solution, we have that the decoupled stresses such as thermal and dehydration and shear stress had very low impact on the protein aggregation when comparing to the non-treated formulation in yellow. On the other hand, the shear stress, the spray drying test, when we are coupling both stresses, we observe a very high aggregation in comparison to the decoupling stresses. Below, what we can observe as well is that the shear stress test formulation turbidity, it's not changing compared to the non-treated solution, which is the stock solution. On the other hand, the spray dried formulation to the right shows very high opalescence, which is corresponding to the aggregation we are measuring by dynamic light scattering. And when we observe that when coupling these stresses on our targeted molecule, we have a higher aggregation. Now we decided to investigate the parameters affecting this aggregation phenomena. which lead us to the next part of the study, which is the study of the parameters impact, such as temperature and shear rate, on this same formulation. For this, we will be using drying temperatures going from 70 to 120 degrees Celsius and to different feed flow rates to generate different shear stress regimes. From the results of this part, what we observe is that the impact of this parameter has no direct correlation for the decrease of the aggregation we are looking to eliminate. And therefore, as we observe no direct correlation, we decided, instead of exploring the optimization of the process parameters, to start the study on the protein formulation. And this takes us to this next part, where we will be studying the formulation impact in the protein and excipients concentration. Firstly, in this part, what we wanted to show and to prove first is that the excipients do not have an impact on the turbidity when spray drying. For this, we generated this formulation without the protein, and it was spray dried to these conditions to obtain a final powder that will be reconstituted. From the results obtained, what we observed is that the excipients after spray drying, in terms of turbidity, did not show any opalescence or an increase on the turbidity compared to the non-spray dried placebo solution. And now, knowing that the excipients are not the cause mainly of the presence of aggregation, we start again the study with our protein formulation. In this case, we formulated 3 different solutions. The first one is the formulation F1.100, and it is the same one used in the previous sections. And from this formulation, what we did is increase the concentration of the excipients, keeping the same protein concentration, to generate formulation F2.100. And from this second formulation, the next step was to keep the same excipients concentration at a high level and reducing the protein concentration. Therefore, this final formulation has the highest concentration of excipients and the lowest concentration of protein compared to the first 2 ones. From the results of this part, in terms of aggregation, we observe that from this first formulation, when we reduce and when we increase the concentration of excipients, we have a drastic reduction on the aggregation of the protein. And after increasing the excipients concentration, if we reduce the protein concentration, what we obtain is again a reduction on the aggregation of our formulation after spray drying. Therefore, what we conclude in this part is that the decoupling of stresses from a formulated monoclonal antibody formulation, in the terms of shear stress and thermal dehydration, when they are alone, they do not have a detrimental impact on the monoclonal antibody, but when coupled in the spray drying process, we can start observing aggregation phenomena. Then, for the study of the parameters and the formulation, the conclusion here is that for a lab scale spray dryer, the most important parameter will be the formulation in our case to reduce or to tackle the problematic of the aggregation during spray drying. And this will take us to focus on the formulation studies for the following part. Now we enter to what we will be calling the formulation improvement of our formulation. It's divided as well in 3 different sections where we will measure the impact on the protein stability. In the first section, we will be studying the protein concentration. In the second one, we will study the excipients and concentration types. Finally, with the information from section 1 and 2. In section 3, we will try the improved formulation in a spray drying process. For these 3 sections, we will have the fixed spray drying conditions that were retrieved from the previous part, and we will all perform at the same conditions. The characterizations for the study of the protein concentration and the study of excipients will be performed, as previously mentioned, in the same way for the powder characterization and reconstituted solutions. Firstly, for the protein concentration study, we realized different formulations going with a protein concentration from 20 to 100 milligrams per ml, and the results in terms of aggregation and turbidity showed that for aggregation, what we can observe here is that if we go even to 75 milligrams per ml, we can observe just a slight and steady increase on the turbidity. But when passing this threshold, we observe a sudden increase on the aggregation present after spray drying. In the case of turbidity, this threshold is found at 60 milligrams per ml. And in this case, what we chose is to stay at a concentration of 75 milligrams per ml, which in this case showed to have a low aggregation present. And this turbidity is something that we can tackle with the manipulation of the excipients in the formulation, which leads us to the next part and section. In this case, we will study the different excipients, concentration, and type. Now, we already fixed the protein concentration at 75 milligrams per ml, and we will have 4 different cycles corresponding to each excipient. In each cycle, one excipient will be variated in concentration while the others remain fixed. The first one corresponds to amino acids, and we'll be using arginine and lysine. The second one studies the pH using histidine and sodium citrate. And the third one, we are using surfactants such as polysorbate 80 and peroxamate 188. And finally, the study of the sugars, such as trehalose and sucrose. As a reminder, all these different excipients have different protection mechanisms for our protein during the spray drying process. For the different cycles, we have 4 different levels of concentration of excipient, going from absence to high. In the absence level, there's no presence of the excipient. The only exception is for the histidine, that it's necessary to maintain the pH of our formulation, which will assure that our protein is still viable before the spray drying process. As well, we use alternative excipients to the ones we were already used in the formulation. In this case, the concentration of these alternative excipients correspond to the medium level of the excipients we were already using. This was with the intention to know if it's the concentration of the excipient or the type of excipient that can affect our protein aggregation. The results of this part showed that the alternative excipients used are very similar to the high level obtained for the excipients already using, but the most important part of this section is that the surfactant should have the highest impact on the reduction of turbidity and aggregation during the spray drying process for a monoclonal antibody. If we go from the absence to the high level, we have a very drastic reduction. What we can hypothesize from this part is that the protection mechanism corresponding to the surfactant, which is the absorption at the surface, we are creating a layer of the surfactant around it. Therefore, we increase the surface coverage, we will have more protection and possible multiple layers around the droplet that replace the protein. And after studying the protein concentration and excipients, fixing the protein concentration to 75 milligrams per ml, and observing that surfactant is one of the most important excipients, we will pass to the improvement of our formulation. For this part, the characterization for the powder will be the same, and for the reconstituted solution, we realize physicochemical studies, and for this reconstituted solution, we realized a stability test for 1 month in the oven at 40 degrees Celsius, recovering 3 different samples, one before the study, another one at 2 weeks, and finally one at 4 weeks. And all the results that will be presented forward are shown for the spray dried and the non-spray dried formulation corresponding to the stock solution. In this part, we wanted to also as well go more in deep in the analysis of the aggregation, and we studied the presence of aggregation phenomena, which was measured by using turbidity techniques and the visual inspection for particles that are visible to the naked eye. As well, what we did was the analysis of the size of the aggregates present in the sample. We did it by using different techniques. For example, dynamic light scattering, which was already discussed, but we also had these techniques such as HPLC, which was used to recover the high molecular weight species present values, and also the capillary electrophoresis LDS, which is used to recover the low molecular weight species, and the nanoparticle tracking analysis to observe the nanoparticles suspended of aggregates in our formulation. And besides the presence of aggregates, we also wanted to study the molecule stability. And for this, we did it for the thermal stability of our protein by using the differential scanning fluorometry. With this technique, what we obtain is the melting temperature of our protein, which is the temperature at which 50% of our protein achieves the denaturation state. And when our protein follows stresses, it can modify its structure. And these changes in the structure can lead to a reduction of the melting temperature. Following this, we have the study of the image capillary selective focusing, which measures the change in the charge of the protein. The charge of a protein depends mainly on its structure that, as we mentioned before, it's affecting when encountering stresses. The materials used for the improved formulation are 4 different formulations. The first one corresponding to the F2.75 we used in previous section, and using polysorbate 80 at a lower concentration compared to the new formulations we are going to show. And this one was used as reference, given that it already showed that it had a decrease on the protein aggregation and turbidity. Now, what we proposed for these improved formulations, we are going from FC1 to FC3. We did a general increase on the excipients concentrations for arginine, trialose, and histidine. And in this case, we as well augmented the concentration of surfactant corresponding to the molecular weights. And we used polysorbate 80, polysorbate 20, and poloxamer 188. We decided to use different surfactants because it proved to be the excipient that had the highest impact on the reduction of our aggregation. Therefore, we wanted to know if different surfactants will have the same effect at the same concentration, or they can improve our reduction of aggregation. In terms of spray drying powder characteristics, what we obtained for particle size distribution for the different polysorbates are particle size distributions very similar, and just having slightly higher values for the formulation of poloxamer 188. The morphology obtained for the different polysorbates, and in this case of polysorbate 80 concentration, are very similar in distribution and in morphology. Now, passing to the aggregation results, which are very interesting for us, what we can observe when we compare different formulations is that formulations containing polysorbate 20 and poloxamer 188 have a better a decrease in the turbidity of the formulation compared to the polysorbate at the 2 different concentrations. In the images below, we have the reconstituted solutions, and to the left, we have the reference formulation, which has the lower concentration of the surfactant. These 3 formulations in the middle corresponds to the increased concentration, and we can see already a reduction on the sopalescence present in the first formulation. For comparison, to the right, we have milky water, and as well, for the aggregates measured by dynamic light scattering, we observe very similar values for the different formulations, and the change they have with the stability test are not very high, as we can observe with these values. But the presence of nanoparticles measured by NTA showed a little bit of a different story. observing that there's an increase during the stability test of the particles present in the formulation corresponding to possible aggregates, but we observe slightly lower values for the formulations improved with higher concentration of surfactant. Now, in terms of low molecular and high molecular species, what we can observe is that the presence of high molecular weight species will lead us to a high increase during the stability test on the presence of aggregates. Therefore, if we have a small concentration, we can end with a high concentration at the end on the protein aggregates. For the low molecular weight species, it's known that the presence of them are not tending to increase in the same way as the high molecular weight species. The presence of aggregate after creating the conditions for the stability test. Nevertheless, for these both species of high molecular and low molecular weights, what we observe is that they are still on the limit that we could expect for the spray drying of a stable monoclonal antibody. And now, in terms of the molecular stability, as measured for the melting temperature I previously mentioned, in this case, what we will observe is that a change between the non-spray dried formulation, which are the first bars, if the difference between the first temperature and the temperature after spray drying is big enough, we can assume we can have slightly molecular changes. In this case, the change in temperature were not drastic, but we could at least observe a small difference between, for example, the first formulation has a bigger difference than the other formulations in the reduction of the melting temperature after the spray drying. And now, in terms of the charged species, basic and acid species, we can observe that, yes, there's an increase during the stability test, but between the different formulations, there is no separating factor that can lead us to think one has producing more or less different acid or basic species. And finally, for the conclusions of this part of the study of the improved formulation, we obtain that the protein concentration working for our formulation to obtain lower aggregation was 75 milligrams per ml, showing that the concentration of the protein has an impact when spray drying. And then we constated that the presence of excipients is critical for the stability of the protein during spray drying, and as well that an increase in the general concentration of the excipients can improve the formulation, especially for the excipient of surfactant. And for the final improved formulation using 3 different surfactants, what we observe is, in general, these 3 surfactants give a same effect or have similar protection effects on the aggregation of the protein. But nevertheless, in the literature, poloxamer 188 is reported to have better results for the stability test of proteins, given that in storage, polysorbates can be oxidized in the long run. And finally, for the conclusions and future perspectives of this work, first of all, I want to point out that the decoupling of stresses, it's a very interesting approach to study the 2 possible stresses, which are thermal and dehydration and shear rate generating during spray drying, in different setups, which allow us to manipulate the different regimes we are generating of temperatures and shear rates. And it's important to note that we can use them for different types of proteins and formulations to compare among them. And for the study of the manipulation of the spray drying operating parameters, we observed that in the conditions obtained in a lab scale spray dryer, by manipulating the different process parameters with this specific formulation, there was no clear correlation in which parameter will reduce the protein aggregation. But on the other hand, what we observe is that the formulation had the higher impact on the manipulation of this presence of aggregation and protection of the protein during spray drying, finding the surfactant as the most important excipient for this type of protein. And finally, we constated that the production of the MAP-A powder formulation during a spray drying process is possible through the manipulation of the excipients and protein concentration to protect the protein against the stresses present. And the perspectives of this work are directed towards the spray drying process for increasing the range of the operating parameters for the future, because now we were using a lab scale spray dryer, which can be constrained for different generation of stresses, and therefore going for larger spray dryers, for example, pilot scale or industrial scale. Then the study of the shear stress threshold to generate a shear stress enough to be able to be sure that our protein is being denaturated, and from there study different regimes of shear stress. And finally, the online follow-up of the aggregation during the thermal stress in the single droplet drying to understand how the different excipients are acting against the thermal stress. For the formulation, the study of the monoclonal antibody without excipients can give us more information that we can compare to the results obtained in this present thesis. And as well, the study of the formulation proposed in the improved phase using another monoclonal antibody to see if different types of monoclonal antibodies are protected in the same way. And finally, the characterization methods. In this thesis, we were mainly focusing on the reconstituted solution characterization. Now we can propose to do a more in-depth study of the powder produced after spray drying. For example, to have a better understanding of the protein structure right after spray drying and before reconstitution by using, for example, techniques such as Raman and mass spectroscopy. And during this thesis, we have the opportunity to present a poster in an international congress and as well to produce two different articles. The first one that is submitted and the second one that is to be submitted. And finally, I would like to thank everyone that was part of this project, and gracias.